So we're going to have a look today, guys, at stereoisomerism. We've already looked in this course at structural isomers, which are isomers which have the same same molecular formula but a different structural formula. So, for example, you might talk about something like butane versus methyl propane. So where we've got the same number of carbons and hydrogen, but they're arranged differently. Stereoisomers are somewhat different, and the particular type of stereoisomerism that we're going to look at is a thing called geometric isomerism. And we're going to look at two types of geometric isomerism. We're going to look at cis-trans isomerism. We're going to look at EZ. So cis-trans is a very simple system. EZ is always applicable, but kicks in really whenever cis-trans we meet more complicated molecules within this area of chemistry. Right, so the first thing is we have certain criteria that you need to meet. So if you're scouring through a molecule and you're looking to find out whether it will actually exhibit geometric isomerism, the first thing that it must have is a carbon-carbon double bond. So anything that doesn't have a carbon-carbon double bond, quite simply, will not be able to exhibit geometric or cis-trans EZ isomerism. The second thing that you do when you go through that structure is you look for the groups that are attached to those carbons. So it's a really good idea to draw the double bond in the molecule out and then draw the four groups at your 120 degree bond angles, just so you can actually see them. And you find out what those groups, I'll just call them A, B, D and E here, just for simplicity's sake. And when you've located and understood what those groups are, what you do is you check that A is not the same as B and that D is not the same as E. Okay, and if you meet all of that criteria that I've spoken about so far, so in other words you have a double bond, okay, and that your A and B are different and your D and E are different, then your molecule will be able to exhibit geometric isomerism. Now the question is why? Well, if I just clear this and I'll draw over here a molecule with a double bond in it. Okay, and if I put on my groups A, B, D and E, A, B, D and E. Now the thing about a double bond is a double bond, unlike a single bond, where if I have a single bond there is complete 360 rotation around that bond. So anything attached here can completely rotate at 360 degrees. Likewise, anything here. A double bond is different in that it gives non-rotation. Okay, so this is a non-rotatable area. So in other words, this group cannot swap with this group, okay, so through rotation. And likewise, D and E cannot change places with each other by simple spontaneous rotation around this region here. The only way that I can swap D with E or A with B is to break a bond, take D off, take E off and swap them around. So that requires bond breaking. Now, so if I look at a molecule, okay, the other isomer of this, so again what I'll do is exactly what I just spoke about. I will take E off and I will swap it with D. So if I now take this molecule, there is no way that I can lift it and superimpose it on top of this one and have all the groups in exactly the same places. D and E, well, D will be up here, D will be down here on this one, and unless I break bonds, which is not allowed, I cannot superimpose them on top of each other. So these two would be isomers of each other, geometric isomers of each other. We have a non-rotatable carbon-carbon double bond, and we have two different groups on either side of that double bond. Now, so that's what you look for whenever you draw out a molecule. So if we take an example of, let's say, a couple of molecules here, and we'll see if we can work out, take the name of them, and see if they actually contain cis-trans isomerism. And then we'll start actually indicating which one is cis, which one is trans, which one is E, which one is Z. So let's take a good old faithful example of but-1-ene, and we will compare that to but-2-ene. And we're going to see, first of all, do these actually have cis-trans or EZ isomerism? And if they do, we're going to draw the cis and the trans and the E and the Z isomers. So let's do but-1-ene first. First thing we do is obviously we'll draw it, and we just draw it normally as we would draw any organic alkene. And we look, does it have a double bond? Well, yes, of course it does. There's the double bond there. And then we go down and we look, we're going to take the double bonded carbons, and we will put our bond angles in, and we will work out what our groups are. So here we have a hydrogen, and here we have a hydrogen. On the other carbon in the double bond, we have a hydrogen, and the group, note, is a C2H5. And we'll just draw it out fully as so. So let's see if it meets the criteria for geometric isomerism. Has a double bond? Yep, fine. Does it have two different groups on either side? Well, if we look at this carbon here on the right, it has a hydrogen and a C2H5 group. They're different, so that's fine. But over here, we have two hydrogens. So this molecule does not exhibit geometric isomerism because it does not have two different groups on this carbon in the double bond here. Right, so the answer for but1ene would be simply no. Let's have a look at but2ene and do exactly the same, work our way through the molecule and see if it can give us cis-trans isomerism. So we'll just draw it out straight chained, make life simple for ourselves. And then we'll go down and some of you may be able to go straight into the bond angle configuration here. Some of you may have to draw this out. So let's look. This is my carbon here I'm talking about with the dot on it, same carbon. I have a hydrogen here, and I have here a CH3. Okay? Here I have a hydrogen, and I have again a CH3. So first criteria, does it have a double bond? Well, of course it does. Second criteria, different group here and here. Yes, indeed it does. Does it have a different group here on the right hand side of the? Yes, it does. So this one will indeed exhibit cis-trans EZ isomerism. Now our next question is, well, which isomer have we drawn? Is this the E, or is this the Z, or the cis, or the trans? Well, in this one we have two groups which are identical on this plane of the double bond above. So therefore, cis means the same. So therefore, this is the cis isomer, and this will be called cis-but2ene. How do we turn this into trans? Because we can never have a cis isomer unless we have a trans isomer. Well, we simply take and we swap our groups around. We keep these ones on this side of the bond the same, and these ones we swap around. And now we have our two groups which are the same on the opposite planes of the carbon-carbon double bond. And this is now what we call our trans but2ene. Okay, and that's how we decide whether we have cis or trans isomers, and then that's how we actually work out whether they are cis or trans. So if we took another example here, so let's take another molecule. Okay, very simple. And let's decide if we have cis-trans. So we'll take our carbons and we'll call this carbon X and carbon Y, and we'll draw carbon X there, carbon Y there. Let's decide on our groups. Well, we have a hydrogen, and here then we have a C3H7. Okay, and here we have a hydrogen, and we have a C2H5 group. So do we have a double bond? Well, of course we do. Do we have two different groups either side of it? Yes, indeed we do. Here, H and C3H7, and here as well. We have our two same groups, okay, on the same plane. So this is our cis isomer, and if I wanted to turn it into the trans isomer, I would swap that with that, or that with that, but not both. Otherwise we'll just have the cis isomer flipped 180 degrees. Okay? Now, and that's really how you work out whether you have cis or whether you have trans. You've just got to work your way through the molecule and decide, does it have a double bond, and are there two different groups on either side of the double bond? Okay, so then we've got to look at some more complicated molecules. So let's take something like okay, so we'll take, let's say, hydrogen and Br. Now, if we look at this, we have now got two different groups on either side of the carbon-carbon double bond, but none of those groups are the same. So on the left or the right, none of them the same. So our cis-trans system is no longer able to be used. This is where we go into our EZ system, although EZ could also be used in the previous examples. So we will take it and we will draw again our bond angles and we will put on our groups. Oops, they are there. And there. This time we've got to use our periodic table to assign priority. So we go get our periodic table and we look at the atomic numbers. Hydrogen has atomic number of 1, bromine has atomic number of 35, chlorine 17, and fluorine is 9. So which one has the highest atomic number here? It is obviously bromine, chlorine here. So these are our two high priority groups. Okay, so therefore whenever they are on the opposite planes, which they are at the minute, that is called the E isomer. Okay, so it will just be E followed by the name of the molecule that the examiner has given you to deal with. If we wanted to turn that into the Z isomer, where our two high priority groups were on the same side, we would simply swap that with that. Okay, and that's how you deal with your EZ whenever the cis-trans doesn't work anymore. If we went back to one of the simple ones that we did at the start, okay, so if we took our but-1-ene that we did right at the very start, okay, and we assigned our priority. This is one we said didn't have cis-trans isomerism, if you can remember. Well, there's a 1 there and a 1 there. So obviously we can't differentiate between those two in terms of priority. So this does not have our EZ or our cis-trans isomerism. Okay, just like it. Okay, as we all sort of already established earlier. If we look at our but-2-ene then, okay, so if you remember our but-2-ene double bond there, we had our CH3 there, our CH3 there, and we had a hydrogen and a hydrogen. So let's go and assign our priority numbers. So here it's a 1, here it's a 1. We go from our carbon in the double bond to the next atom out, so that's a 6, and here is a 6. So we have high priority here, high priority here. That's our two high priority groups on the same plane. So that is Z, and of course it will be Z followed by the name, and the name is but-2-ene. That will be Z but-2-ene. And of course again, to turn it into E but-2-ene, I simply swap that with that. So that's how you do it, pretty straightforward. We look at one which is, I suppose, fairly complicated, that I don't think you'll come up against one that's more challenging at A-level chemistry than this. So if you can understand the principles behind this one, you should be able to understand the principles behind all of them. So let's take a molecule that the examiner has perhaps given us. We'll draw it out fully because it's easier to deal with when you draw all the bonds in these. Okay, so a bit more of a scary looking molecule, but the principle to solve the problem is exactly the same. So we take our first carbon here and we go out to the next atom along and we look at that. That's a carbon, so that is 6, and this is also a carbon here, that is 6. So we can't use those because they're both the same number. In that instance, we go to the next atom out. Okay, so the next atom out here is a carbon here, and we have two hydrogens direct, so it's the ones that are directly attached to this 6 carbon. So we have carbon, which is 6, hydrogen 1 and 1, and we list those by order of atomic number, 6, 1, 1. And now we go down to this carbon, which has 3 hydrogens, so we have 1, 1 and 1. So we have 1, 1, 1, and hopefully, therefore, you will be able to work out that because of the 6, 1, 1 versus the 1, 1, 1, this 6 here wins the day, and we have our high priority group above the plane of the carbons here. Then let's go over here. So let's go again. We go to the atom closest to the carbon in the double bond. That's the carbon here, 6, and here, same again, 6. So can't use those. They're the same number. We go to the next atoms out. So here we have oxygen and 2 hydrogens. So we go 8, 1, 1. And down here we have oxygen and 1 hydrogen. So therefore you might think, okay, well, 8's cancel, the 1's cancel, and that leaves me with this one left over. But we need to be careful. When we have something with a double bond in it, we actually list it twice. Okay, so therefore going from what we might have thought the top group was a high priority, in actual fact 881 is higher priority than 811, so my high priority group is on the bottom of the plane. Therefore my 2 high priority groups are on the opposite sides of the plane of the double bond, so this is going to be my E isomer. So you just write E followed by the name of that molecule. Okay. Right guys, so hopefully there's a few of those in your notes that you can use, lots of examples, but if you apply the principles that I spoke about there, both for calculating out cis-trans and then moving into EZ, geometric isomerism, you really shouldn't have any particular problems with solving the problems that come your way at AS level.